So next we're going to talk about something called an electric field and also talk about some very simple electric circuits. So it turns out the fact that charged particles exert force on one another at a distance allows us to define something called a field, an electric field specifically, that's associated with charge. So this is similar to a gravitational field. So we know that on the surface of the Earth, if I hold the tennis ball some distance above the surface of the Earth and I let it go, the tennis ball falls towards the Earth. And that's because of the gravitational pull of the Earth on that tennis ball. But more specifically, we say that surrounding the Earth there is this gravitational field. So no matter where I put the tennis ball above the surface of the Earth, it will always be attracted and pulled down towards the Earth. We have a similar situation with magnets. If you take two magnets and you bring them next to one another, they, as a kid, if you play with magnets, they exert forces on one another. They don't have to be touching, but they exert forces on one another. So the same thing is true about electrical charge. And so surrounding a single electric charge, we say that there's an electric field. And so here's an example of what a positive charge electric field would look like. So there's a positive charge in the center, and the electric field radiates outward from that positive charge. These electric field lines tell us the direction of the field, and more specifically, it tells us the direction that a positive charged particle, the force that a charged particle would exert from the other particle. I didn't say that very well. So if I were to take and put a positive charge right here where my laser pointer is, it would experience a repulsive force from the other positive charge, and it would be directed away from that charge. And so those lines describe the direction that the force on a positive charge, the direction of the force that would be exerted on a positive charge. On the other hand, we have a negative charge here, and we notice that the electric field lines, instead of radiating outward, radiate inward. And so if I put a positive charge at some location away from that negative charge, it would experience an attractive force towards that charge. And so those lines tell us the direction that positive charge, the force, the direction of the force that positive charge would experience. And so we have a simulation that we can look at. So here is a positive charge, and I can use a sensor to determine the direction of the electric field. So if I put my sensor at this particular location, you can imagine that this sensor consists of just a positive charge. So positive charges repel. That sensor experiences a repulsive force away from that positive charge. Now, the closer that the sensor is to the positive charge, the greater the force would be, and the further away that you get, the smaller the force would be. And so that arrow is describing not only the direction of the force that would be applied, but also the size of the force. And so we say that there's an electric field present because no matter where I put the sensor around that positive charge, it always experiences a force. So a single charge all by itself creates an electric field. And so these arrows here are describing the direction that the electric field would be, so it radiates outward from that positive charge. Now, if I replace that with a negative charge, and I use my sensor is basically just a positive charge. And if this is a positive charge and that's a negative, it's attracted. And so the direction of the force would be along the line connecting them, but an attractive force. And that's also the direction of the field. So again, if I get closer, that value gets larger. If I get further away, it gets smaller. And no matter where I put that sensor or that positive charge around the negative one, there's always this attractive force. So the electric field, so we say there's a field around here that I can detect, and the direction of that field is always radiating inward, and that's what the direction of those arrows is actually showing. Now I can also put a positive and a negative charge next to one another, and we can see what the electric field would look like. So here now when I move my sensor around, right? It looks a little bit different. Right? And that tells me the direction of the field. And so if I go ahead and I show the electric field lines, that's what they would look like. They sort of point from positive to negative and then they curve around. And if I changed that to 2 positive charges or 2 negative charges, we could see what that would look like. Right, that one is a little bit harder to see because it seems like they still radiate outward. So charges by themselves, a single positive charge all by itself, creates an electric field surrounding that positive charge. And the reason that we know the field is there is because we can take a sensor and we can place it at any particular location and it will experience a force from that charge, and those arrows are just telling me the direction of that force, right? So if I put it over here, there's the direction of the force. If I put it here, if I put it right here, right, those lines are parallel to one another, telling me the direction. So here's some other pictures that are representations of what the electric field would look like. Here's the positive charge and the negative charge. The positive charge, the electric field sort of radiates outward. For the negative charge, it comes inward. But because I have both charges together, those two fields that are created from both of those charges can be added together, and we get this effect where it goes from the positive to the negative. And then if I have two positives, we get sort of that same thing where the electric field would want to radiate outward, but when they're close together inside here, the field would actually cancel. So if I put a positive charge at the very center here, it would be repelled from the one on the left and repelled from the one on the right, and essentially there would be no force at the very center. We can take charges and put them on a set of plates so that one plate at the top is positive and the other plate is negative. And what we notice is it produces an electric field which is very uniform in the sense that all of these are equally spaced and they are pointing in one particular direction. So this is one way to create a constant electric field. When the lines are closer together, that means that the electric field is stronger. So the closer you are to like these charges, you have a larger density of points. It's a larger field, and as you get further away, those lines spread out and the electric field is smaller. So the main thing to keep in mind here is that when you have charged particles, charges exert force at a distance, and anytime you have force at a distance, these non-contact forces, we associate fields with those forces. So we have gravitational force, which is non-contact force. There's a gravitational field. We have electric force between two charges, or Coulomb's law. We have an electric field, and then we're going to see the same thing with magnets, where magnets can exert force at a distance, and we will see something called a magnetic field. So one everyday application of this idea of an electric field is how microwaves actually work. So when you heat something up in your microwave, what you put in your microwave is something that contains a high concentration of water. So all food contains water molecules. And it turns out that water molecules are called polar molecules. And what that means is that the symmetry of the water molecule is such that the hydrogens that are attached to the oxygen, the H2O, two hydrogens and one oxygen, are not equally spaced from one another. So it kind of looks like Mickey Mouse with the ears where are the hydrogen and then the oxygen down here. And so it appears as if you've got some separation of positive and negative charge. And because of that separation of positive and negative charge, when you place something that contains water in a microwave, here's my water molecule down here, a microwave produces a fluctuating electric field. It's an electric field that changes direction, and it also changes size. And that's what this is down here. The yellow line on here is the electric field. And at any given instant in time, it's increasing, it's decreasing, it's changing direction. And so when you put a charged particle in an electric field, just like if you have a single charge and then you put your sensor next to it, that's our charged particle, it experiences a force. And so because the electric field is fluctuating and because this water molecule has separation of positive negative charge, it's experiencing a force. And that's a vibrating force because the electric field is essentially vibrating. It's changing rapidly direction and size. And so that rotation or that vibration of the water molecule creates energy. And that energy, that kinetic energy, turns into thermal energy. And that thermal energy is what causes your food in the microwave to actually change temperature.